Welcome back. This is an Aleks training video on predicting relative boiling point elevations and freezing point depressions. If you have regular water, it freezes at 0 Celsius and boils at 100 degrees Celsius. That's not by accident. That was designed that way. They simply took the freezing point and boiling point of water and made it 0 and 100, and then a degree is simply 1/100th of that space. If you add anything to the water, if you add salt, for instance, to the water, it's not going to freeze at 0. It's going to freeze lower than 0. It's not going to boil at 100. It's going to boil above 100. So adding stuff to the water gives a boiling point raise, and it also depresses the freezing point. It's why you put not regular water in your radiator in your car, but you put ethylene glycol, which is antifreeze. It will let it get lots hotter, because your engine is going to be way hotter than 100 degrees, and you don't want all your water to boil and make a bomb. So you need something that's going to boil at a higher temperature so that your engine doesn't explode it. So we are going to be using molality to do this, and we did molality the other day. Molality is moles over kilograms of solvent. And it's not just moles of solute, it's also moles of anything that breaks down. So let's say you have salt. I put salt in water, it breaks apart into sodium and chloride. You're going to have, if you had 1 mole of salt and you put it in water, you're going to end up not with salt anymore. You're going to have 1 mole of sodium and 1 mole of chlorine. And since it breaks apart, molality actually counts in the particles. It's the moles of particles divided by the kilograms of solvent. So if you break something up into 2 parts, you have to double the number of moles you have. If it breaks apart into 3 parts, you triple the number of moles. So let's give you some examples. Your question, by the way, is you've got some glycerin, which doesn't break apart. You've got some potassium iodide, which breaks apart into 2 things. You've got some hydrochloric acid, which breaks apart into 2 things. And they're asking, what's the freezing point and the boiling point of each? Okay. And I think what they're actually doing is saying the boiling point would be the highest, 1, 2, 3, 4, 5, and the freezing point would be 1, 2, 3, 4, 5, with 1 being the lowest and 4 being the highest. I think that's what it is. All right. So let's look at the weight of the water first. You have 100 mils of water, okay, in all cases. So how many kilograms is that? 100 milliliters is a kilogram. It gives you the density of water. So the density of water is 1 gram per milliliter. Okay, so 1 gram per milliliter. So that means you are going to have how many grams in 100 milliliters? Okay, well, if 1 gram is 1 milliliter, then you're going to have 100 grams in 100 milliliters. That makes sense. Okay, so 1 gram per milliliter is density, so you're going to have, in 100 mils, you're going to have 100 grams. How many kilograms is that? Okay, so you'll have 100 grams, and you'll have 1,000 grams in a kilogram. So you're going to divide by 3. So it's going to be 1, 2, 3. You're going to end up with 0.1 kilogram. That's going to go on the bottom of your molality. Remember, it's moles of solute, moles of particles of solute divided by kilograms of solvent. So you're going to have 0.1 kilogram on the bottom. So I need to find the number of moles of each of these guys in order to the molarity, or molality. So let's do the first one. The first one is going to be the glycerin. And the glycerin, if I add it up, is going to be 92.09382. So I need to I'll take 83, or 8.3 grams. Its molar mass, I added it up, was 92.09382. That's going to give you 0.09013 moles. Okay, now I ask myself a question. Does glycerin break apart? It's C3H8O3. It's not all of them are nonmetals, which means that they're covalently bonded, they're not ions, they don't break apart. So this glycerin would just dissolve in the water in single pieces. So if I have 0.09 moles, that's all I'm going to have is 0.09 moles. All right, so my first guy is going to be 0.09013 moles over 0.1 kilograms. So let me do that. 0.09013 divided by 0.1 kilograms. Okay. And that gives me 0.9013 molal. Okay, so that's my first guy. My second guy is going to be what? The potassium iodide. All right, so the potassium iodide is going to be Ki, and the Ki, I have 8.3 grams, and its molar mass was 166.0028. That gives me 0.05 moles. Now I ask myself a question. When I put a salt like this is left of the side of the periodic table is positive, the I is negative, so it breaks apart into K's and I's. So that breaks apart into two things. So I'm going to have 0.05 moles of the potassium. I'm going to have 0.05 moles of the iodide. So I'm going to have to double this. So it's 0.05 times 2. So I'm going to have 0.1 moles. Okay. So I'm going to have 0.1 moles of particles. So when I have 0.1 moles of particles over 0.1 kilograms, I'm going to have 1, not 0.1, 1 molal is the Ki. Okay, that's your second one. The third one is the hydrochloric acid. Okay, so the hydrochloric acid, so HCl. So I have 8.3 grams. It's going to be, I added that, it's going to be 36.461. Gives me 0.2276 moles. Now I ask myself a question, does it break apart? Okay, I've got H and Cl. Now it is all nonmetals, but it's an acid. Remember, H plus chlorine is hydrochloric acid, and it does break apart. It's one of the 6 strong acids. It completely dissociates, and it dissociates into ions. So it dissociates into H plus and Cl minus. So I do have to double this. So I'm going to take 0.2276, double it, and I'm going to get 0.4552 moles. And then I divide it by the 0.1 kilograms, divided by 0.1, and I get 4.552 molal. The water, the pure water, doesn't have any molality because there's nothing dissolved in it. Okay, so water will be 0. All right, let me write it here beside so we remember what we've got. This is molality, remember, moles over kilograms of solvent. So the glycerin we had as 0.90. The potassium iodide we had as 1.0. The hydrochloric acid we had at 4.6. And the water was at 0. Okay, so let's do boiling point first. Boiling point is going to be 100 when the molality is 0. It'll be 100 degrees. As the molality goes up, the boiling point goes up. All right. So what's going to be the lowest? Well, the lowest would be at pure water. So I guess that's a 1. So that would be the lowest. And then as it gets higher and higher and higher, molality, it's going to get a higher and higher and higher boiling point. So the 0.9 would be 2. The 1.0 would be 3. and the 4.6 would be 4, and that's the highest. And it goes exactly opposite. All right, so the highest freezing point is the one that's least affected by the dissolved stuff. Okay, so the highest freezing point would be closer to 0, and it would be 4. Okay, so this would be highest. And then it gets colder and colder and colder as it gets away. So the next highest would be here. Okay, the next highest would be here. And then the lowest would be the one with the most dissolved stuff. So that's 1, and this would be the lowest. Okay, I hope it helps.